Alright, so let's get started with the practical. Now, I know that the theory for this was very fast. Unfortunately, it's one of those things where I would much prefer to explain this in line by line while coding it, rather than in a theory presentation. So let's go ahead and do that now. I'm going to start out by grabbing our ambient, duplicating this and moving it over. And let's just rename this to 3A Specular. We're going to go ahead and create some more components. So I'm just going to duplicate these two, 3A Specular and 3A. Alright, let's go ahead and open up our Specular shader. So we're going to start out right at the top by calling our shader something like Unity cookie /tut /beginner /3A properties. We're going to add in a few more properties this time. We're going to have color. So there's one that we had before. This is going to be 1111. Now we also want to have a spec color so that we can change the color of our specular component. This again is going to be a color. And we also want to have another variable called shininess. Now I'm not a fan of the name shininess. I like to call it like specular power, but unfortunately Unity likes it to be called shininess. This sounds a bit weird because when you're using the shader, not Unity, but if you need to use any external lighting models, it's expecting something called shininess, and you have to give it that. So I don't know who came up with that term at Unity, but it's kind of annoying. They probably should have used something a little more, programmy. It's a very loose term. Anyways, that's my rant. So we've used float for that instead of color, and float will just give us a little box that we can type in a number. So let's create our subshader and fallback diffuse. Okay, let's start off with our tags. We want to have light mode equals forward add, and that's just, remember, so that we can, forward base sorry. Alright, so remember that's just so that we can have our directional lights work in the latest version of Unity. And we can have our pass, CG program, and be moving through this a bit faster now that we've learned a bit more. Pragma, Vertex, Pragma, Fragment, Frag, just so Unity knows where to find our Vertex and Fragment programs. User defined variables. So we're going to be using uniform float for color, uniform float for spec color, uniform float shininess. So again, we want to have our Unity defined variables. Here we are going to have uniform float for light color 0, and now we can move on to our structs. So this is all familiar stuff so far. So the structs we're going to have, and this one here is going to have inside it float for vertex position and float 3 normal. So the same as the previous shader. Struct vertex output, float for pos SV position, float for cull is going to be color. So it's exactly the same as the last shader. Alright, so let's start the vertex function. Vertex output, vert, and we're going to take vertex input as base. And I'm also going to quickly set up the fragment function. So the fragment function, we are just going to be doing the same as before. And we're going to be doing a before frag, vertex output, I is going to have the semantic color, return I.cull. Alright, so that's the same as before. So we're right up to the point of everything we've already done already. Now it's time to start fleshing things out a bit. Let's go ahead and start this out with a vertex output O and a return O. We're going to O.position. Right, so this one here is going to be Unity matrix MVP v.vertex to get that one there working. And we're also going to have O.cull with float 4, and this is going to be something, 1.0. Right, so what are we going to do in terms to lighting? What do we need? Well, to calculate our lighting, we need to have a normal direction, a view direction, and a light direction. So let's go ahead and start creating them. Vectors, and we're going to start with float 3 normal direction equals, and we'll go float 3 view direction equals, and float 3 light direction. And light direction, of course, goes with a float of 10 equals 1.0. Alright, so let's work through these. So for our normal direction, we want to do the same as before. We're going to take a multiplier of the float 4 v.normal 0.0, and we're going to multiply that by the world to object transpose. We take through that one there, and then we take the XYZ of that, and we also want to normalize it. Alright, so that's exactly the same as the previous shader, the view direction. Now the view direction is something new, we haven't done this one yet. What we're going to do is we want to get our camera position and our vertex position. So what we have is, what we want to do is grab our multiplier that we have down here, just copy and paste that, and grab this, and we want to subtract this from the position. So world base camera pos.xyz minus that. Now the position is a float 4, so we need to introduce a fourth component of this, 1.0. Alright, so just to explain what's happening here is we have the camera position and we have the position of the vertex. What we're doing is we are effectively calculating the distance between them. Our view direction is going to be whatever direction the camera is facing minus the position of our vertex. That makes sense. So it's kind of calculating the distance, but it works to calculate our rotational vector of our camera relevant to our object there. So we could use this just as is, but what we have here is we have a float 3, so we need to make sure we change this to be a float 3. So let's go through, change this to a float 3, and while we're at it, we might as well normalize this. I like to normalize everything, just to make sure I don't get any artifacts. I should really bring up an example of artifacts without. Anyways, so that's our view direction. If we just take a look at our view direction, probably won't look pretty at all, or if it even works, but we'll just see what we get. So let's go ahead and go Unity cookie, and we've got a problem there, so I'll fix that in a moment. Unity cookie to beginner 3 as regular. Alright, so at the moment we have a error here saying incorrect number of arguments to numeric type constructor. This here is a bit of a pain. It means that we have specified something incorrectly. Right, so what we've forgotten to do is we've forgotten to take this inside here, this float 4, we've forgotten to take the XYZ component. So Unity doesn't know which components to take. Reload that, and there we go, it is now working. Alright, so you can see how that's kind of changing colour depending on our light direction, which is pretty cool. Or our camera direction, sorry. It's coming out pink because it's not. There's no camera view within these little icons, so it's not quite sure what to do with that. Right, so that's how we calculate our vertex. That's pretty cool. So let's go through and calculate our light direction. Just come through here, and I'm just going to call this here lighting. Alright, so we have our light direction equals normalize world space light pos 0.xyz. Alright, so same as before, what we're going to do now is take our diffuse and specular reflection. So let's go grab a float 3, diffuse reflection, float 3, specular reflection. Let's calculate these. Right, so diffuse reflection is going to be the same as before. We are going to grab the attenuation times the light color. So this is light color 0.xyz, and then we want to multiply this by the max of 0.0 and the dot product. So this is going to be a dot product of normal direction and light direction. So that's the diffuse. That's exactly the same as what we did before. Just to reiterate of how that works is we're doing the dot product with the normal against the light direction, and that returns a value of 0 to 1 from the light direction across the normal, depending on which direction the normals are facing. So normals are facing the light, it will get a value of 1, facing away, it'll get a value of 0. And that's how diffuse lighting works. Now the max just gets rid of any negative numbers, and the attenuation times the light color just calculates the lighting intensity and the color of the light itself. Alright, so moving on to the specular reflection. What we're going to do is we're going to write this piece by piece. So we're going to start off with reflect of negative light direction and normal direction. So we're reflecting that light across the normals. And let's actually just have a preview, see what this actually looks like. I haven't actually done this before, but what I'm going to do is I'm just going to show you what each component looks like as we build it up. Hey, that looks really interesting. But you can kind of see where that specular highlight is going to go, where all those colours meet. that will be where the specular highlight will be. So that's the reflected colours, which creates some really interesting effects because it's a vector we're displaying. That's why it's in weird colours. So now that we've got that one there, we're going to do a dot product. So we're going to do a dot product of this against the view direction. Doing that in the wrong spot, I'm going to put that up there. Dot product of this one here against the view direction. Take a look at what that looks like. Alright, so I know quite what we want, but you can kind of see how it's changing based on our camera view. Let's take this a little bit further. So we've taken the dot product and we'll reflect it. What we need to do now is we need to do a max of 0, because at the moment you can kind of see how we're getting some on the reverse side. So we need to get rid of that. So let's do that now. 0.0 dot product of this. Alright, so there's no negative numbers, but there's still lighting on the back side. We'll focus on that in a bit, but that softened that edge a little. What we need to do now is multiply this by a power of shininess. So we can do that in a bit. Let's first deal with the getting rid of that stuff on the back. So I'm just going to take this one here. So this is our Lambert lighting model. And take that, and we're going to multiply it by our specular component. Alright, so you can see now that it only appears where it should. It's a little bit dripping down the back there. That's fine. That'll be fixed when we do the next bit. Alright, so that's kind of gotten rid of that problem. What we need to do now is we need to go ahead and use a power function of this to the power of shininess. Alright, we should reload this now. You can see we get a much brighter specular highlight. And what we can do is we can adjust the fall off of this. So we can make it really bright, really subtle. It's up to you. And this is just the specular component. So that's just specular that we're seeing right now. Alright, so what we need to do is we need to add these together. So let's go float 3 light final equals the diffuse. Actually, we can just add these. Diffuse reflection plus specular reflection plus the ambient, which is Unity light model ambient, I think. I hope. And we're going to go light final times color. Alright, so there we go. So we have a specular highlight, which follows the lighting around. Alright, so what we need to do now is we also need to put in a component so we can control the specular color, which I just noticed it was also called color, so let's call that specular color. So in here we need to go continuation times underscore speccolor.rgb times that. Alright, so if we just come through here and reload this, we can now give it something like a red specular highlight if we want. Right, that is great. Alright, so I've made a bit of a mistake here. When we copied across the position here, I forgot to change the Unity matrix. The Unity matrix MVP, this is something that we use when we want to store the position of the vertices. However, what we want to do is, up here, we need to use the object to world transpose, so that we can get it in world space to match the world space camera position. So we're just converting the vertices into the world space rather than the Unity transpose. So what we get now is we get a much more accurate specular reflection. I just noticed that it was slightly off. It was off by about 0.3. Something small, but something very important, that you make sure that you multiply your vertex by your object to world transpose, not the Unity matrix MVP. That was my mistake entirely, and I apologize for that. But yeah, so just make sure you have that in there. Alright, so this is the shader done. So what we're going to do is I'm just going to go through and talk about each one of these individually, and then we're going to move on to the next stage. So of course we give it a name, properties, these are all familiar apart from the new one where we had a float, and that's just that little input box. Alright, light mode, forward base, that's just so that it will work because we're using forward rendering. Alright, CG program, the pragmas, all familiar, that's familiar, these are all the same as what we've done previously. Alright, so the normal direction, we will normalize our normal direction, and it is just the normal multiplied by the world to object transpose. That's all it really is. The view direction, we will multiply the object to world by the vertex so that we get our vertex position in world space. and then we subtract that from our world space camera position to get our view direction. And all the float 4s, float 3s, and normalize, that's just to get it so that it will work without any artifacts, and work with DirectX 11 of course. Alright, so that's stuff we've covered previously. Light direction, attenuation. The light direction is world space light position 0 to x by z. That makes sense. Diffuse reflections from the last video. Now specular reflection, what we do here is we multiply the attenuation by the specular color by the Lambert lighting model, so that it will fade off over the edge, and then we multiply all of that. So this is just this piece here, this is just colouring it, fading it off. Now that one there, we multiply it by the power of our specular. So just coming in here, we reflect the inverse of the light direction across our normal direction to get our specular reflection. If I just remove that negative, I'll just show you what happens if we don't have a negative there. Alright, so but what happens is it's probably on the, it'll be on the other side of the model. So that's why we have that. Paste that back in. Alright, so we take the dot product of the reflected vector against the view direction so that we can get that in that 1 to 0 range, or 1 to -1 I should say. And that way we can sort of preview it, it'll show up on the model. And we take that to the power of shininess. Hopefully that'll make sense. If you're a little bit stuck there, it's a bit confusing. If you're stuck, let me know and I will help you out. Alright, and then what we do with light final is we add the diffuse and specular and ambient components together, and then we multiply those by our colour to get the final result. So, with our vertex lit shader done, it is time to move the specular and the Lambertian shading to the Fragment program. Let's go ahead and do this now. Okay, so back in Unity, here is our vertex lit shader, and you can tell it's vertex lit by this very harsh lighting around the side. You can actually see faces. So what we're going to do is going to duplicate this over, and I'm going to rename this one here 3B specular, because this is going to be our pixel lit. Let's duplicate our material as well, 3B, so I'll drag that one there over, and let's go and open this up. Alright, so this is going to be the same as the specular one at the moment, so I can close that one. But we're just going to go through and edit it. So we're not going to rewrite this one from scratch, there's very little point in that. We just want to edit it and show you how we can move things from the vertex function to the fragment function. So it'll stop working on every vertex and it'll start working on every pixel, or every fragment I should say. Okay, so the first thing we want to do is we want to come down to these structs. Now the vertex input is fine, we don't need any more there. What we do want is the vertex output. So I'm going to delete color because we want to calculate that in the fragment function now. And let's just add in a couple here. So I'm going to grab pos world and normal dir. Alright, so pos world is going to be our world space position that we calculate over here. You could actually just do it for the view direction. For now we're going to do this calculation in the fragment function, but when we get to the end of the series and we start talking about optimization, we'll talk about how we can do little things to optimize like this. Alright, so the other one is a normal direction, so this one here, we're going to keep that one. Okay, so what we need to do is assign these to a text coordinate, and we can do that with text coord 0 and text coord 1. Now remember that text coord 0 and text coord 1 stores your UV maps when you bring in your model. Now we use those when we want our textures, but because we're not dealing with any textures at the moment, we can just overwrite what's in them. And you can overwrite any of the text coordinates that you like that you don't need. So in this one here, we're just going to overwrite text coord 0 and text coord 1. If you're working with, say, an Xbox 360 shader, I believe that goes up to text coord 12. I could be wrong with that, I haven't made any shaders for an Xbox 360. Different hardware has different amounts of text coords that it can use. Some only have 4, some have 12. I think the PS4 has a ridiculous amount that hasn't been released yet, so I have no idea. Alright, so let's continue. Let's go down to the vertex function. Alright, so let's put in a couple of gaps and see what do we want to keep. Well, I want to keep these two, because we need these 3 lines in every single vertex function. That's how that Unity knows what it's returning, how it knows the position. Now the other ones we want is we want o.posworld and o.normaldir. And normaldir is going to be a float 3, not a float 4, because you can see it there. Alright, so let's start with posworld. We just take this one here, copy, and actually no, not that one, we want our position and copy that up here, and we want to grab the object to world. There we go. So you want this to be a float 4, not a float 3. So this one here, we'll just return the pos world. So this pos here, we can't directly access that within the fragment function. I don't know why, it's kind of irritating, but every time I try and access the pos, it throws an error. This might be a Unity 4 thing. So we just return what we want, the pos world, and we can then access that here. Okay, so normal direction. I'm just going to copy this thing, copy, and paste. Alright, that's great. So that is our normal direction. So we don't need any of this down here. So what we're going to do is start working on the fragment function. I'm just leaving that up there so that we can copy it for now, by the way. Okay, and let's do that now. Let's just copy all of this, or let's just cut it, I should say, and just paste that into here. Fantastic. Alright, so we have this. How do we deal with it? Well, first thing we want to do is we want to make sure that we're returning this float 4. We're not assigning it to anything. Now our normal direction, because we use these down here, we're just going to rename them. So let's call this one here i.normaldir. The view direction is going to be slightly different. We're going to cut out this one, and we're going to subtract from this i.posworld xyz, and then the rest of this should be working fine. So it's quite easy. All we've done is we have rebuilt these, and we've copied the entire lighting model. We haven't edited it at all. I don't think this would work, but we're going to try this. Yep, there we go. So we'll start off by assigning this. We have a whole lot of errors. So there's things like, expected token 0, conflicts, a whole bunch of errors here, and what we need to do is we need to just go through and it's just basically figuring out which bit is going where. So let's go through and work through these line by line, just to make sure that we have no errors. So you can see this one here, there's not going to be any errors here unless normaldir had a float 4. So we already changed that. This one here, view direction equals normalize, and first thing I can see is counting the brackets. So we can have 1, 2, 3 opening brackets, 1, 2 closing brackets. And we could add in another bracket over here, but what I want to do is remove this float 4. Remember, we're assigning this to a float 3 now, so we don't actually need this. So we have a float 3, let's go ahead and remove this float 3 as well. We don't need that. Let's see if that works. Alright, so still nothing working. So that's when you move down and start working with other things. We don't want the comma. Alright, so you move down and you start working with these. So these ones here, we copied all of these from the previous one. So what could possibly be wrong with these? I can tell you now, actually nothing. There is very likely to be nothing wrong with these ones here. So it just leaves us these lines to work with. Alright, and I can actually see that there is a semicolon I've missed up there. You gotta watch out for those semicolons, they're very irritating. And there we go, that wasn't too bad. I was expecting a lot more errors. Alright, so there is our new lighting model. So you can see it does kind of look like it's working on the vertices rather than the pixels, because there's a little bit of, jumping around there. But that's it, actually just jumping around the facets. So this isn't actually a smooth surface, so it can't render it as a perfectly smooth surface. But you can see definitely on these sides here that it is in fact now a pixel shader. Now I will let you know that the pixel shaders are a lot more computationally expensive. There is a lot more calculations, whereas if I just flick this open, with our Vertex lit shader, we might have this vertex function run maybe 300 times, whereas the fragment function might be run, 2000 times or whatever. It does take a lot more calculations, but it does look a lot more nicer. When you're writing shaders for your games, if it is a minor object, then make it vertex lit. Leave the pixel lit objects for your hero props and things that look weird. So if you have something that just doesn't look right, then it doesn't look right being vertex lit, then you can go ahead and make it pixel lit. But try and get away with as much as you can. We'll be talking about this a little bit more in the last part when we talk about optimization.